Bianca Viray from the University of Washington.
Okay, thanks very much for having me. I'm just gonna find the chat window so I can keep an eye on it. If there's any questions. Yeah, thank you very much for the introduction, Eric, and thank you everybody for having me. So I'm gonna speak on isolated points on curves, and just before starting, I want to acknowledge that I currently live and work on the traditional territories of the Duwamish and Coast Salish peoples. And if you're interested in seeing what traditional territories you are on, you can go to this website, nativeland.ca. Also just wanna maybe spotlight, in February, every day of February, mathematically gifted and Black spotlights a Black mathematician. Today's honoree is Annie T. Randall. And if you go to the website and click read more, it gives you a nice interview of the person. And they also post on, I think, like every social media thing. So you can look at it that way if you want. Okay, so all of my work that I'm going to be speaking about today is joint work with Abby Bourdon, Özlem Ejder, Yuan Liu, and Francis Odumodu. And when you put our initials together, it spells Belov. And so despite the convenient placement of where the vowels are, this is not someone else's name. This is just the initials for all of our last names. So I will label all of our results that way. Before I get started talking about what I mean by isolated points on curves, let me just first tell you what it means to me as an arithmetic geometer when I talk about points on curves. It might be different depending on your point of view. Okay, so I want to start with this warm-up question. And hopefully will be within everyone's wheelhouse. So is there a right triangle with every side length rational? You guys can vote with your reactions if you want. No? Can we have one thumbs up? Yes, okay, so yeah, so we want every side length rational. So we take our triangle and we put it down. So we're not getting, yeah, okay, maybe the way that I phrased it, I'm not asking for every possible rational number to appear as the side length, but just is there one with some rational numbers? So I want a triangle, which I label A, B, and C. And then we know by the Pythagorean theorem that this is if and only if I have some non-zero rational numbers, A, B, C, such that A squared plus B squared equals C squared. So I don't get every possible thing satisfying every possible value of A, B, and C satisfying an equation like this, but there are some A, B, and C that do satisfy this. And in fact, we get infinitely many. And there's sort of an easy way that we can see that we get infinitely many, which is I pick my favorite Pythagorean triple, so maybe 3, 4, 5, and then I just take the edge of the triangle and scale it, and that gives me infinitely many. But even if you mod out by that, we still get infinitely many. So we get infinitely many distinct Pythagorean triples that are distinct up to scaling. Okay, let's step it up a bit. So now I want to fix a positive integer n and ask, is there a right triangle with every side length rational and that has this specified area n? This is not a rhetorical question, it's an actual question. Anyone want to guess?
No.
So I heard a no. Yeah, so let me go through it a little bit more. So the question, I think, well, one, it's not immediately obvious, as evidenced by the answers. And also we know, you can sort of see that it's a little bit more subtle. So if I didn't specify my integer ahead of time and just asked you whether this exists for some integer, then of course you can take one of the examples we had on the previous slide and plug it in. So if you take 3, 4, 5, then we get area 6. So for 6, it works, but what about for n equals 5 or n equals 4? It's not as clear. So let's again draw our picture, and then we write down the equations, what this means. And then if you make this change of variables, which seemingly comes out of nowhere, but if you make that change of variables, then it's just equivalent to finding an x, y, and z that satisfy this single equation. Okay, so this is relatively simple, but more complicated than the one that we originally countered. And this is an interesting question. This is called the congruent number problem. So if there is a right triangle with these properties, then n is called a congruent number. And not every integer is a congruent number, so it depends on n. You can look up the sequence of them in OEIS. But one thing that's interesting and is not obvious in this case is that when there is a right triangle with area n, then actually you get infinitely many of this side length with area n. And that is, I think, not at all obvious because now your scaling trick doesn't even work anymore. But we still get infinitely many. Okay, so what do these triangles and these configurations have to do with what I'm talking about, points on curves? Well, we considered x squared plus y squared equals z squared, and this y squared z equals x cubed minus n squared x z squared. Those are what I call curves. They define nice algebraic curves in the projective truth space. So what do I mean by a nice algebraic curve? So by nice, I'm just like everything that you would want something nice to be. So I mean compact, one-dimensional, that's what I mean by curve, complex manifold with no singularities. And the fact that it's algebraic means that we can define it. So if I looked just from this perspective, I can think about that analytically and give complex charts and then gluings between them. But because it has this avatar as an algebraic curve, it's given, that means it's given by some vanishing of an algebraic equation. So it's points which satisfy some algebraic equation. And in the nice case, those algebraic equations have rational coefficients like they do in this case. And when they have rational coefficients, then you can ask about algebraic properties of the curve. That's not something that you can see or talk about just purely from the complex analytic perspective. But since these equations live over Q, you can ask about solutions that live in Q, and that makes sense as a question. So because they have this algebraic presentation, we can ask about rational points on these curves, and that makes sense. And we consider these solutions where we want them not all to be 0. So generally, I'm going to take homogeneous equations, and then I'm going to consider the solutions not all 0 and up to scaling, just like I did before. So, and yeah, so this condition means that it can be a difficult question to figure out where there is a solution, whether there is a solution or not. Okay, so what are some things that we can ask about rational points on curves? Well, we could ask whether there's a rational solution. And then on the first 2 questions we looked at, we saw that there were actually infinitely many solutions. It's an amazing result of Faltings that this is very rare. For curves to have infinitely many solutions, it only happens if the curve is sufficiently simple geometrically. So let me just state, so if you have a nice algebraic curve over Q, so some system cut up at polynomial equations, this curve can have infinitely many solutions over the rational numbers only if the genus is at most 1. So if we took our algebraic curve, we looked at it as a complex manifold and we counted the number of holes. As soon as it has more than 2 holes, then you know that you can never have infinitely many points. Okay, so this is an amazing theorem, a landmark result in the field. And this sort of really nicely encapsulates a philosophy of arithmetic geometry, which is that we expect geometry to control arithmetic. So this geometric property of the genus, which can be read off purely from the complex manifold without paying attention to the arithmetic structure of the curve, that influences the curve's arithmetic behavior. Even though it's a purely geometric property, it has nothing to do with the curve's avatar given as an equation with rational coefficients. It still influences whether that equation can have infinitely many rational points. And this is sort of the dream we want. Like, we would like a complete understanding of how geometry controls like all arithmetic properties on any set of equations. So we have this for curves in terms of whether or not you can have infinitely many points. This is a great theorem, and this is sort of what we dream about the state of the world, our state of our understanding being. Okay, so the theorem is actually even better than this. It actually holds over any number field. So it holds over any field that's a finite extension of Q. So any finite extension you want, we can take. And so no matter how, you're like, okay, well, I don't get any points with rational coefficients, but let me I'll throw in like the square root of 2 and the cube root of 5 and the 17th root of 7, and I'll throw all those in. But still, if my genus is too big, I will never find infinitely many solutions over those points, over those fields. Okay, so why do we consider sort of the rational numbers, Q, and number fields together? Well, one reason is that we just have noticed that they behave similarly. So often if a theorem is true over the rational numbers, then it is also true over number fields. So we should stick them together. But if you didn't come from number theory and you hadn't learned all those theorems, another thing that you might think about is that in number fields, those are elements of number fields are basically the elements of C or of the real numbers that we can write down in finite space to arbitrary precision. So a rational number we can encode completely just by its numerator and denominator. But a rational number we can encode because square root of 5 we can express to arbitrary precision using something like Newton's method. So just carrying around that this satisfies the polynomial x squared minus 5, which we can like list in finite space, we can compute that decimal even though it doesn't repeat. We can compute it as far out as we want and on the fly as we're going. So that's something, if you want, that's another way to characterize number fields. Okay, but if you look at it from this information theoretic point of view, then there's another natural set that comes up, and that's not just taking number fields, but maybe infinite unions of number fields, maybe of a fixed degree. So let's just look at an example. If I take the union of all quadratic number fields, so that's anything that can be expressed as a plus b times square root of c for a and b rational numbers, and c I can take to be some square free integer. Well, describing anything in this set, I basically need to specify 2 rational numbers and a square free integer. That's all I need to satisfy. So sort of being able to describe this whole union basically takes the same amount of information as describing a cubic number field, maybe q adjoint cube root of 2. Okay, this is worse for doing algebra. Like I can't take an element, I can't take 1 plus square root of 2 and take like 7 minus I and add those together and still end up in this space. So we can't do as much nice algebra, but we can still carry things around. And if you think about going back to our question about rational solutions on curves, we do algebra on the point, like coordinate by coordinate, to check that it satisfies this equation. But given 2 points on the curve, we're not usually interested in combining those coordinates in some algebraic way. They're just like separate elements of the set that don't interact. So instead of just considering the points on the curve over q adjoint square root of 5, we could ask and be given, in some sense, the same amount of space for the collection of points on the curve that are defined over some quadratic number field. And that's, so this is like, I want to describe points over a quadratic number field. I'm agnostic about which quadratic number field I take. I like all of them equally. I have no favorite children among the quadratic number fields. So I just want a way of getting all of them. Yeah, that's what I said. Okay, great. So how do we talk about this? How do we talk about the points on the curve defined over some quadratic number field? Well, that brings us to the notion of what's called a degree D point on the curve. So a point is degree D if, so I take it, it's a point on the algebraic closure. So sort of each coordinate lives in some number field. And then it's a degree D point if the coordinates generate an extension of degree D. Okay, so this is just what I was talking about on the previous slide, more precisely defined. Okay, let me, so we don't have to scroll so many times. Let me just jump to. Okay, so here are some examples. So first, I could just take a rational point. So in this case, for the first curve here, I could set x to be 0, I could set y to be 0, and then I could set z to be 1. All of those are defined in the rational numbers. That's a degree 1 point. But I could do other things more complicated. I could set x and z to be rational numbers. So I plug those in. And then if you look at this equation, you see, okay, if I plug in constants for x and z and solve for y, then that becomes a quadratic equation in y. And so this is a degree 2 point. It's actually defined over the extension q adjoint square root of minus 23, but I don't really care that there's a minus 23 there. Just care that I took a square root. I could play the same game by instead plugging in numbers for y and z, and then I solve for x, and then that's a cubic equation for x. And this is an irreducible polynomial, so that does generate a cubic extension. Not every example is as nice as this, where you set some number of the coordinates to be rational, and then just one defines an extension. So if you look at this example, it just miraculously happens that when you plug in square root of 6 to the right-hand side of the equation, just turns out you get a square times 6. So when you take a square root, again, you don't have to adjoin another square root. You just adjoin the square root of 6. And so this is a degree 2 point as well. Okay. Any questions on this? This is basically just like looking at points over the union of all degree D extensions. I should say I would much rather everyone follow my talk than I get to the last slide. So you should feel free to interrupt at any time, even if it's to go back like 3 or 4 slides. I would be very, very happy to do that. Okay. So like I said, if you're concerned about looking for points on the curve from this information theoretic perspective, that you want to know, okay, well, what are the points that I can write down, to finite precision in this amount of space, then you don't want to look at whether they're points over a fixed number field. You care about looking at points at degree D points. So you can ask, okay, is there an analog of Faltings' theorem where instead of looking at infinitely many rational points, I ask for infinitely many degree D points? That's still an arithmetic property. So, I mean, should be a different theorem. So we don't know that it's still going to be controlled by the genus, but the philosophy of arithmetic geometry predicts that there should be some geometric property hopefully we can figure out what it is, that controls this arithmetic behavior, whether or not you can have infinitely many degree D points. Okay, so let's start with examples. I love examples. I feel like that's the best way to get to know things. So let's start with a genus 2 curve that's a double cover of P1. So algebraically, I can write this. So you can think double cover of the Riemann sphere, and I pick 6 branch points. I'm going to pick 0, 1, 2, 3, 4, 5, and so I can write it algebraically this way. So this is a genus 2 curve. And Faltings' theorem tells me that because the genus is greater than 1, this only has finitely many rational points. And even more than that, it's not just finitely many rational points, it's finitely many points over any finite dimensional extension of Q, so over any number field. So Q adjoins square root of 2, square root of 3, square root of 1,079,000,000, like whatever. I still only get finitely many points, and even if I took higher extensions. But you can see quite clearly in this example, we get infinitely many degree 2 points because I play the same trick that I did with the examples on the previous slide. I just set X to be some rational number and I plug it in, and then I get a quadratic equation for Y. And so it's always defined over a quadratic extension. And this is a problem that persists even if the genus gets bigger, because I can just add more and more branch points to my double cover. And by adding more and more branch points, I make my genus go higher and higher and higher. I can get arbitrarily high genus that I want. And everything else that I said still holds true. It has finitely many points over any number field, but infinitely many quadratic points. So we see very quickly that the genus is not a fine enough geometric invariant to tell us about this arithmetic property, that we need to dig deeper into the geometry of the curve to understand what controls this arithmetic property. And so that's also giving some evidence that having infinitely many degree D points is a much more subtle arithmetic property than having infinitely many points over some number field. Okay, so let's look geometrically what's going on. So I think of this curve as being one-dimensional. So I'm really drawing sort of the real points of this picture. Many of you who are more complex analytic in your inclinations are probably, you know, looking with disgust at this picture of my Riemann sphere and a Riemann surface covering it. Okay, so what's happening? So the base, this is my cartoon of the base of P1, and this is the double cover, representing the double cover over it. You can think of this as taking a slice of the Riemann sphere if you want. Okay, so the base has infinitely many rational points all along. That's what these blue lines are telling you. Some of these rational points are special for the map. Those are the branch points. I had rigged it so that they're all rational. That's not necessary, but. And so above those, there is this unique point above them. But for any other point, say for this one, if I look above it, I get 2 distinct geometric points. And one thing that I get looking over the rational numbers is that these points are like glued together by the action of Galois. So because this map is defined over the rational numbers and this point is defined over the rational numbers, Galois has to fix this fiber. So one point, it might not be rational, but it has to get sent to the other thing. It doesn't go anywhere else. Okay, and that's true for all of the other rational points on the base that aren't these pink dots. And in fact, even in the spaces where I don't have any black circles, I still have these X's tied together there. These ones are just ones in the picture where I get an imaginary quadratic extension, where I take the square root of a negative number as opposed to the square root of a positive number. But they're still quadratic points. Okay, so what can happen? Well, it could happen that sometimes there's some coincidence that these points are actually already rational to begin with. So Galois doesn't even preserves not just the pair, but preserves each element pointwise. And that could happen for a few different fibers over here as well. But Faltings' theorem tells me that it happens only finitely many times. That all the rest, the infinitely many remaining rational points on the base, have to stay Galois conjugate. That they are not defined over Q, they're really defined over an honest quadratic extension. So this is the picture of the infinitely many degree 2 points we get. And I mean, it was sort of suggested in the algebraic point of view, but I think this picture really drives it home. It's not really from the curve. I mean, it's kind of from the curve, but it's really from P1 and from the map. Like, we're getting these infinitely many points because I'm just moving along the fiber and I'm getting infinitely many points on the base. Okay, so this is sort of a thing, as we saw, that I can do for any degree 2 map to P1, not just this one where I've rigged all the branch points to be at integers. Okay, so this happens a lot in math. We find like a nice construction, which gives us this thing that we're looking for. And so then we want to give it a name. So I'm going to say that a degree 2 point or a degree D point that arises in this way is P1 parametrized. And you should think of it as just, I have a picture like this. So really, what does it mean? It means, so a degree D point is P1 parametrized if there is a map of the same degree, a degree D map, where that point maps to a rational point. So that's exactly what's going on in this picture. And from this definition, this picture just shows you that all of the x's that I've drawn, they are P1 parametrized, because the x's means that there are degree 2 points. That's what my cartoon meant. And this is a degree 2 map, and they're all mapping to rational points. So this picture shows you that all of these x's are P1 parametrized. It takes a little bit more work, but you can also show that the dots, the circles, are not P1 parametrized. They're P1 isolated. So meaning you can't move along a P1. And so the picture doesn't show it. So to show that they're P1 isolated, we have to show that there's no degree 1 map. So we need no degree 1 map. But now here, that we can do because our curve that we're starting with is a higher genus curve, and there's no degree 1 map from a positive genus curve to a genus 0 curve. So that shows us that our points are P1 isolated. Okay, and once you have a P1 parametrized point that gives you this map, then you have this map, and from Hilbert's irreducibility theorem, we know that having a map like this will give you that you have infinitely many degree D P1 parametrized points. So the argument I used on the previous slide basically said, okay, well, there's only finitely many degree 1 points by Faltings. If you have a D that's much larger, then you can't just throw Faltings at the problem to rule out the lower degree cases, but you can instead appeal to Hilbert's irreducibility theorem, which tells you that this map will always give you infinitely many degree D P1 parametrized points. Okay, so now we have this nice characterization of how this occurs. We understand as soon as we have the map, we get infinitely many degree D points, and P1 parametrized points gives us these degree D maps. And so then we ask the question, we have this construction, is this the only way? So if you rewind back in your head, the explanation I gave you, and you have a very accurate recording, you might notice that really all I used about the base was that it had infinitely many rational points. I didn't really use that it was P1. I mostly just used that it had infinitely many rational points. And then if you rewind even farther back, you remember at the very beginning of the talk, I mentioned Faltings' theorem, which gave us two possibilities for when a curve can have infinitely many rational points. It can be genus 0, and then it's P1, or it can be a genus 1 curve with infinitely many rational points. So we can actually run the same argument, just the same cartoon, except instead of, oh, that's not what I wanted to do. Well, okay, instead of this picture, instead of thinking that that's P1, you should think that that's a genus 1 curve with infinitely many points. Okay, so let's give another definition. So what I want you to think is it's just the same definition as before, except here at the bottom, I'm allowing a genus 1 curve. Watch that this is a genus 1 curve with infinitely many Q points. Okay, a genus 1 curve with infinitely many points has at least 1 point, so this is also known as an elliptic curve. And an elliptic curve is a one-dimensional abelian variety. It turns out that in this case, something a little bit more complicated can happen. You can have a cartoon like this, where you don't just consider a one-dimensional abelian variety, but you have a positive, higher dimensional abelian variety. So that's why here I have the name AV parametrized, AV for abelian variety. It's not a huge deal what the difference is if you're not familiar with this type of math. You can really, for the whole talk, it will be fine for you to just think of this picture, just only pay attention to the picture on the bottom of the slide. If you're really interested in what I mean precisely, you can read the definition at the top of the slide, but I'm going to pretend that it's not there. Okay. So just focus on the cartoon, but we have to consider sort of two possibilities for the base. One is that it's P1, and one is that it's a positive rank abelian variety. Okay. So I'm going to say that a point is parametrized if it can move along either one of these types of families, and then that will give me infinitely many points. And that it's isolated if it's not that, so if it can't move along either case. Okay, so how should we think about the difference between these types of points?
Sorry, can I ask a question?
Yep.
So you said that these two cases of like P1 and abelian variety, could it be the case where like the base might be some other higher dimensional variety which has infinitely many rational points? Or does that boil down to the first case again?
It will boil down to one of the other two cases.
Okay.
Yeah, so that will be maybe the next slide is a precise statement of this, but yeah, we don't have to go any farther than these two types of parameter spaces.
Okay, thank you.
Okay, so let's dig into the difference more. Well, parametrized, that was really what we defined, right? And parametrized, you saw from the definition of parametrized like comes with a witness, right? It comes with this map that's showing you that it's parametrized. And we know whenever you have a definition where you're sort of handed something that comes with it, that gives you extra tools that you can use to understand what's happening. And that happens for parametrized points. This map, or the analog of a map in an abelian variety case, gives you some extra leverage, and it has some geometric implications. So I like to think of this as a parametrized point has some geometric shadow. There's sort of a geometric property that has to happen when you have the existence of one of these parametrized points. So they're better understood. We have more tools to understand them. Okay, what about isolated points? what do we know about them? Well, not really anything else. I mean, we know that they're not parametrized points, which doesn't give you much leverage. It's about the non-existence of these maps. Okay, if you push me, I can maybe say a little bit more. So one thing that's really, I think, amazing is that there are only finitely many isolated points on any curve. And this may not seem that surprising because we already talked about Faltings' theorem, but I want to remind you that the definition of isolated point, it doesn't have a bound on the degree. So this is a condition, something that you can define for any point over Q bar. And curves have infinitely many points over Q bar. There are tons and tons and tons of them. Basically, you put any algebraic coordinates you want for any of them, and then you solve for the others. You always get algebraic equations. But only finitely many of those points are ever isolated. So that, I think, shows that these points are really special points on the curve. And I think if you made me guess, or even a random arithmetic geometer, you made them guess, they would probably tell you, well, probably for some definition of most curves don't have isolated points, that this should be a rare thing to have happen. This is a guess. I have no idea in what sense of most, what is the strongest thing that we could hope for. But these points, curves with these points should be rare. Okay, but now I feel like this proves my, like emoji reaction is even more justified. The things that we know about it actually show that these points are even more mysterious. Like, what does it mean? What are these special points that are on some curves, but not on most curves? I don't know. I think this makes them really interesting. And I wish I knew more, but I do not yet know anymore. And so this goes to Samya's question. Another reason why I argue that we care about the distinction is the parametrized point. A parametrized point gives us the analog of this Faltings 83 theorem that I asked for at the beginning of the talk. So if you have a nice algebraic curve over Q, then this curve has infinitely many degree D points. If and only if there is some point that is parametrized. Okay, so you could argue, well, this isn't really an exact analog because I told you Faltings' theorem is an example of geometry controlling arithmetic. And the definition of a parametrized point, well, that included some arithmetic conditions. This map had to be defined over K. And in the case of AV parametrized, I wanted the abelian variety to have infinitely many points over K. Those are arithmetic conditions, and that is true. But the original Faltings theorem was also an only if statement. If you souped it up to an if and only if, there would be some arithmetic input on the other side. So you can also weaken this statement to an only if and replace this parametrized point with a purely geometric condition using these geometric shadows that I alluded to before. So this characterization does give you a way to recover this exact analog. And basically this comes from a stronger theorem of Faltings about rational points on subvarieties of abelian varieties. This statement hasn't been pulled out of it as far as I can tell before our paper. So we write the proof in our paper, but basically it's just apply Faltings' theorem over and over and over again. So, okay. All right, that's just, and I think this is probably the strongest thing that you can say about isolated points without any assumptions on the curve. If you don't want to assume something about the curve, then I don't think you can do something stronger than this, because even though we expect most curves not to have isolated points, you should be able to rig curves to have lots of isolated points, just like we can rig curves to pass through many rational points. So I don't think we can get much better than this. Okay, so you might ask, where do we go from here? I mean, I motivated this definition, which is one that we came up with, and told you that I characterized. Still, the only thing that's our work I'm attributing as an epsilon. So hopefully there's more coming. So this is what we know about curves. So let's think, if you're an arithmetic geometer and you want to look at the arithmetic of curves, say you're starting grad school and you go to study it, like what do you do? How do you get started? What do you decide what to look at? Like, do you just show up, you talk to your advisor and they hand you like this sack of curves and they're like, hey, pick one out of here, that's your thesis, good job. Well, as you might guess, that's not how we study curves. They're just not just arranged in some sack. Well, we've seen that's a very fruitful point of view in a lot of modern algebra is we don't just study the objects, we study things in their category. So we study objects together with how they relate to each other, with the morphisms among curves. So if we want to know what happens with isolated points, we shouldn't just look at a standalone curve and ask what happens. We should ask, okay, well, how do they behave when you move between curves? What happens with isolated points? So we start with some morphism between the curves and we want to know what happens. And what we show is that if you have a point on the source that satisfies, you should think of this as a genericity condition, that its degree is as large as it can be given the constraints, then being isolated pushes forward along the map. So if you're isolated on the source, then your image is isolated, assuming this genericity condition. So that tells us sort of in this whole category of curves, what should we expect to happen as we sort of propagate these isolated points through these maps. Okay, so now we know what happens in our two building blocks. So we know what happens on curves, we know what happens on morphisms, and then where do we go from here? Now, do we again just grab out of the sack, maybe the curve together with the maps? Well, not exactly. So we want an analog of a curve that really will tell us anything. What are the all-powerful curves in our space? Well, there's not one curve to rule them all, but there are special ones among those curves. And those are curves which are themselves moduli spaces. So these are curves which encode the arithmetic of other curves. So if we understand what's happening on this one curve, we can use its moduli properties to tell us what's happening on a whole bunch of other curves. So those are ones we're really, really interested in, our favorites, if you made us admit to it. And moduli spaces, so they're parametrizing some kind of objects, and they normally come, you can sort of refine and refine and refine those properties. So they arise in some towers. So the ones I want to focus on in my last 5 to 10 minutes are these ones x1 of n, which come in this tower, which is infinitely wide and infinitely tall. So it's parametrized by non-negative integers and it's arranged by divisibility. Okay. And so what does our theorem say? So we look at this tower, we know that in this whole tower, each curve has only finitely many isolated points. But if we want to understand the arithmetic of the tower, we have to understand what's happening on infinitely many of these curves. So even though this tower goes infinitely high up, what our theorem says is, okay, we have this genericity. If this genericity condition is satisfied, these isolated points should trickle down. So even if they're high up in the tower, they cast a shadow or they move down or they propagate to somewhere low in the tower. That's sort of the philosophy that our theorem is saying, that presence of isolated points should be able to be detected low down in the tower. Okay, but this is really a should, because for our theorem to apply, we have to know that the genericity condition holds for the point. And we already know that the point we're trying to apply to is kind of special because it's an isolated point, which we already know are special points. So there's this tension where we want to apply this theorem to special points, but in order for it to apply to them, sorry, we need to know that they're some sense general. Okay, so let me go to here. Okay, so what are these curves x1 of n, and why are they special? Why are they the curves that rule them all? So they give us information about the arithmetic of elliptic curves, which, as I said on one of the previous slides, but you might not have caught, it's a genus 1 curve with a fixed choice of point. Okay, what is that fixed choice of point by us? We have this donut, we have some point on it. We can make a cuts along this donut, along the 2 generators of the fundamental group, and we can open up this torus to something that looks like a subset of the complex plane. And then this subset now just inherits the group structure from the complex plane. So I can just add points together on my torus like I did on the complex plane. And this addition is well defined from my choice of base point. So it depends on the point I choose, but still, once I fix the point, it has a group structure. And x1 of n basically tells us about the arithmetic of torsion points on elliptic curves. So the points on x1 of n encode pairs of an elliptic curve together with a torsion point of order n. Okay, if you are friends with any arithmetic geometers, you've probably heard that we get really excited about an elliptic curves and also about torsion on elliptic curves. But you also might have heard people say, oh, torsion on elliptic curves, we know everything there is to know about that. And it's pretty much true. We have this amazing theorem by Morel. It's a uniform boundedness theorem, and this is like in our heart of hearts what we dream all a uniform boundedness theorem should be for Diophantine geometry. So it says if you fix a positive integer d, then for any elliptic curve over a number field of degree d, so any degree d extension of q, and then any elliptic curve you take over that, the torsion on that elliptic curve is bounded by a constant that depends only on d. So the torsion cannot be very complicated at all. It's quite constrained. Over q, there's only 15 possibilities for what the torsion subgroup is, and we understand them completely. Okay, so now let's take this theorem and see what it tells us about isolated points on this tower, x1 of n, because that's what we were interested in. And so if you put Morel's theorem into this sort of moduli space box and apply a few other theorems with it, what it tells you is that if you have an isolated point high up in the tower, then its degree has to grow. So as you go higher up in the tower, the isolated points become higher and higher degree. And that's bad news, because that means that they're harder to find computationally. So it gets much harder to work with number fields of higher and higher degree. So if you're going up, you're like climbing up this tower, searching and searching, searching for them, not only do you have infinitely high up to go, as you go up, your job gets harder and harder and harder and harder to do it. But this is exactly complementary to the philosophy that our theorem says. Our theorem says, don't bother looking high up in the tower. It says those points, they may be up there, but you should be able to see that they're there low down in the tower. So just figure out where they are low down in the tower, and then then the places where they can be are very constrained high up in the tower. So, okay, so that's what I want to see. Okay, so that's the philosophy of our theorem, but then we actually have to check, okay, in this tower, if we have isolated points high up in the tower, do they satisfy this genericity condition? And so that's what we study. We have to prune our tower a little bit, so we chop it off, so it's only finite horizontally, but still infinitely tall. And then what we show is that if you look for a certain kind of isolated points in these towers, so-called non-CM isolated points. The CM ones we sort of understand by other ways that correspond to elliptic curves over Q, that those type of isolated points can always be detected, that our philosophy is true. We can verify there is this line where you can detect them below that line. And the line is, it's not just an existence, we give a pretty precise formula for what it is. And then I'll just end just by commenting, we can conjecturally, we don't need the bound. We don't need to chop it off horizontally, but yeah, that's only assuming a conjecture, which a pretty large conjecture about Galois representations of elliptic curves. All right, well, that's what I wanted to get to. So thanks for your attention.
Questions for the speaker?
Oh, I guess I had a quick question about this. You were saying that you have this precise formula. How effective is it? Are the numbers that you get in your precise formula gigantic? Are they small? Are they? I don't really know what to ask about it. So
they're reasonably small, but okay, I'm not going to remember off the top of my head. But basically, we get so we get that you have to consider integers n. So for the x1 of n of the form 2 to the something times 3 to the something times a prime that's less than or equal to, I think, 37. And then for each of those numbers, the bound on the power of 2 and the power of 3 depends on which prime that you have there. So I think it's on the order of 100 possibilities of n. But the problem is that I don't know how computationally feasible it is to look at all of those curves because the genus grows very quickly with n. And the problem gets already when you're like past genus 7, the problem is really hard. And I think we get some, I don't remember off the top of my head, but definitely above 50. We have genera above 50. So it's like both small, but also high up enough the tower that we need some new ideas.
Any more questions? Can you say anything about heights in this world?
We haven't looked at all. So our proofs are really sort of Galois representation theoretic, and then also just like pushing around like our morphism theorem is just lots of diagram chasing, like following these maps to the things that parameterize them and trying to pull them back or push them forward. Or so yeah, it would be nice to have a better sense of what should happen with these points, but at this point for me, like there's not enough examples, and I don't know like what kind of statement that you would want. So we don't get anything out. I think there are interesting things, but I think it's also new enough that it's unclear like what you should hope to be able to say. But if you have ideas, that would be great to hear them.
Yeah. All right. Any more questions?
Yes, I may have a question. Is there a way to actually characterize what the isolated points are, other than what you've done? I mean, is there a hard characterization of them?
I don't know any besides like what we have done. So I should say, so similar ideas of like what these special points are have been floating around the literature, we're, I think, the first people who really like pinned it down in this particular way. Normally people were mostly concerned with like, what is the first degree where you get infinitely many points, and what are the isolated points sort of below that bound? Whereas this sort of gives a characterization for any degree that you want. Yeah, I mean, I guess that's part of what's hard about the study of rational points is like there's no real characterization besides like you can write it down over the rational numbers. That's sort of exactly what makes it hard to do anything with them. Yeah, so I think it would be great if there were another characterization, but I'm not super optimistic that there is one.
Okay, thank you.
More questions? All right, let's thank the speaker again.